Alright, in this video we look at another example of reversing the order of integration. Sometimes, reversing the order can feel like busy work. You just feel like, why are you being asked to set up the reverse order of integration? Is it just twice the amount of work? If you set one of them up, why not just go with that one and try to work with it, right? So what we're seeing here is that when you set up a double integral of a function f of xy, and let's say you choose the ordering dy dx, and you've chosen to set up your x and y limits, and you might have chosen the reverse order. Maybe some people just prefer to have dx come first and then dy, and you saw that the x limits came along and then the y limits, and one of these maybe set itself up easier for you. Okay, the thing to keep in mind about double integrals and integrals in general is that there are always two parts to the problem. There is the setup phase, right? And then there is the evaluation phase. So from a certain point of view, maybe these integrals are both the equivalent amount of work to set up. So there's really no preference of one over the other. So the setup may be equivalent in work to each other. But when it comes to the next step of evaluating the integral, this is where we see how good the order chosen was. Okay? And so here, for example, is a double integral that has been set up as a dy dx problem. Okay? And they are saying in this problem to reverse the order of integration and then evaluate the integral. Okay? So you may be thinking, like, why don't we just do this integral that has been given, integrate dy, and then move on with life, right? Well, one of the difficulties and things to remember is that if you try to do the dy problem, we need to integrate then the sine of y over y, which means that you may need to integrate a function, in this case sine of y over y, and integrate with respect to y, and that function may not actually have an antiderivative that you're familiar with. In this case, this antiderivative is called the sine integral. So this is quite different from integrating sine of y, and its antiderivative is negative cosine of y. Sine of y divided by y does not actually have an antiderivative that we know about. And then you're like, well, maybe sine of y over y doesn't have an antiderivative, but I should be able to maybe find the integral from x up to, what is it, pi? Maybe the definite integral will be better. Okay. But remember, to do a definite integral, you needed to know the antiderivative so that you could plug in the top and bottom limits. So if you don't know the antiderivative, it makes finding the definite integral difficult. So what we're seeing here is a reason that we must, when it comes to the evaluation part, reverse the order of integration, because if we set up the problem as a dy dx problem, it's not actually doable. Okay, so let's move on to this problem, right, and try to reverse the order of integration. So what you were given, the given order of integration is the double integral from x going up to pi, sine of y over y, dy dx. This was the given order of integration, and x was going from 0 up to pi. So we should probably call out that this is y is equal to x up to y is equal to pi, x is equal to 0 up to x is equal to pi. Now, anytime you're asked to reverse the order of integration, it would be a good idea, and I really don't know how to do it otherwise, to sketch the region of integration. So what we're seeing is that y is going on the bottom from y is equal to x on the bottom up to y is equal to the line pi on the top. And then x is going on one side from 0 over to x is equal to x is equal to pi. So how did I know to stop this green line right where I did? It's because when x is equal to pi, when you plug y is equal to x and you substitute in y is equal to pi, then when x is equal to pi, then that'll tell you that y will also be equal to pi, which was that top line. So we can see that the lines are intersecting at x is equal to pi, and the bottom limit was the line y is equal to x up to the top line y is equal to pi. So if we want to reverse the order of integration, we need to go the other way. We need to go from left to right. Okay, so let's set this integral up now. We would set this integral up as the same integral, the same function, sine of y over y. That doesn't change when it comes to reversing the order. And x is going on the left from 0 up to x is equal to y on the right. If y is equal to x, then that means that x is also equal to y, and that's on the right. And then we need the values of y where this is possible. Y is going from 0 up to y is equal to pi. Now, the claim is that this integral, now that we've set up the integral in a reverse order of integration, that this can be evaluated because we are now integrating with respect to x, and sine of y over y are functions of y, so they are constants, and therefore can come out in front of the integral. And now we're just integrating 1 dx, which is equal to x evaluated from 0 to y, and so we'll get sine of y over y multiplied by y minus sine of y divided by y times 0, which is just equal to sine of y. And now that we're able to get past that first integral, we can now do y is equal to 0 up to y is equal to pi of sine of y, and then integrate with respect to y. The antiderivative of sine of y with respect to y is negative cosine of y, because the derivative of cosine is negative sine. Negative sine makes sine. Evaluated from y is equal to 0 to y is equal to pi. So minus signs, should be very careful here. It would be negative cosine of pi minus negative cosine of 0. Cosine of pi is negative 1. Cosine of 0 is 1. So we got negative 1, which is 1. Negative 1, which is 1. So the answer is equal to 2. Okay. And that would have been possible to check in Mathematica. So if we bring up a palette, writing assistant, there were 2 ways to set up this integral. Oops. 2 ways to set up this integral. Okay. There was the original ordering, which we were going to have some trouble with, right? But a computer might not have trouble, because computers maybe know some integrals and how to evaluate some integrals that we don't. And so when we had the original ordering, y went from, let me see, remind myself, y went from x up to pi, and x went from 0 up to pi. But we can set that up in a reverse order of integration. And to do that, we had to sketch the region. And now we're going to integrate the same function, sine of y divided by y. Put parentheses around that function. It'll help the computer separate the function from the dA. And sorry, we're doing dx dy. And x is going on the left from 0 to x is equal to y on the right, and y is going from 0 up to pi. And if you ask the computer to evaluate both of those, you will get both of the answers to come out to be 2. Okay. Now, the next question is, we always have a third step, right? There is the setup phase, there's the evaluation phase, and then there is the interpretation. So we have to interpret. What did we just compute? Okay. And here we're seeing is if you would like to practice typing these commands in, there is a region plot command, and you can see that I'm doing region plot 3D. We're saying just setting up all the limits that we've got. Y is bigger than x, but y is less than pi. X is bigger than 0, but x is less than pi. Basically, I'm just taking the 4 limits of the integral. You can see y is bigger than x, but y is less than pi. That's what this x on the bottom and y on top of the integral is. X is bigger than 0, but x is less than pi. And then how do we bring in the function? We haven't really pointed that out so much yet, but this function, we're trying to say the function is the surface, and we want to be below the surface but above the xy plane. So that's bigger than z equals 0. And that region, when you plot it, will give you this solid region right here shown. Okay? And then if you just plotted the surface all by itself, just sine of y over y, it would be this surface here. And we have found that that double integral has the interpretation of the volume below this surface, but above the region that's drawn in the xy plane. So the interpretation of this double integral is a volume. So the volume of this region is equal to 2. Okay? We will look at more interpretations of double integrals in the next video.